So today we're going to be joined by Dr. Jessica Stromberg and Dr. Carsten Laukamp from the Mineral Resources Division of CSIRO based in Perth, Western Australia. Today's going to be quite informal, so we're going to keep the chat open if you want to ask any questions along the way. We do have kind of breakout sessions for questions and answers, so we will keep track of that. And we have got a break midway through just for you to go and grab a coffee and for us to resume. So without further ado, I'll hand over to Jess and Carsten.
Hi everyone, my name is Jess Stromberg. I'm a research scientist at CSIRO. I've been there about 2.5 years. You may tell I'm not Australian. I moved to Australia from Canada, where I was working as a postdoc at the University of Winnipeg, working in hyperspectral data, and did my PhD at the University of Western Ontario, where I worked on Archean gold systems in the Abitibi and worked underground as a production geo as well. And so my time at CSIRO, I've been working a lot with the NVCL, the National Virtual Core Library, which is why you're all here today, but also in other projects integrating hyperspectral and geochemical data for exploration and kind of ore body knowledge type stuff, developing new workflows in that and working on some new technologies. So it's been a ride. Got to work on a couple of interesting projects and looking forward to talking to you all today about some of the work we do in the NVCL. Carsten.
Yeah, thanks, Jessica. Thanks everyone for joining today. My name is Carsten Laukamp. I originally started a geoscience career in structural geology and metamorphic petrology, but then about 12 years ago, I moved to Australia to do a postdoc at James Cook University in Queensland, that is, in Townsville. And so they dumped me into the Mount Isa inlier, which is one of the worst or most complicated pieces of crust on the Earth, probably. And then I fell in love with remote sensing, which requires reflectance spectroscopy or understanding of that. And I learned that on the fly, basically, then, and worked together with CSIRO. And then then I was convinced I should join CSIRO directly, maybe. And I'm now with CSIRO since 10 years, 11 years, looking after all kinds of spectral sensing from the microscope, drill core, airborne, spaceborne sensing, and trying to see how we can use this technology for exploration and mining. So mainly applications in the resources sector, basically. And yeah, as Jessica said, we're going to give you an introduction into the National Virtual Core Library project that we're both involved in. And we're doing a number of workshops as part of this National Virtual Core Library project. And after that introduction, Jessica is going to show the Discovery Portal, AuScope's Discovery Portal, where you can access some data, and she's going to show you what we can do there. And then we're going to provide some more details about some background about hyperspectral mineralogy. Why do we care? Why do we do it? What can we do with it? And then Jessica is going to show us some applications, an example Greenfields case study from WA. And I then continue as well with another case study from WA about some lithium deposits. Yeah. Then I guess that's all enough for the introduction, other than if Joe or Lewis want to say something else, or Jessica?
I just wanted to say quickly, just for data reasons, this is being recorded. And if you have an issue with that, leave yourself with your camera off and yourself muted, and you can drop any questions that you have to either me or Joe in the email that I sent the link out to, or in the chat here. But if you're all right with that, then that's absolutely fine. But yeah, I think crack on as far as I'm concerned.
So I hope you can see the presentation screen, not the presenter's screen. Let me know if that's okay.
Good.
All good, super. Okay, so the Australian National Virtual Core Library, accessing Australia's continental scale drill hole dataset. We thought we start this workshop basically with a focus on the NVCL, because it's also, we're doing lots of workshops as part of the National Virtual Core Library. We do lots of training for universities, for industry, for geological surveys on how to use hyperspectral data and what all these hyperspectral data mean. And the National Virtual Core Library was, the idea was put together about maybe 15 years ago. There were some former colleagues of us from CSIRO, namely John Huntington and Lou Whitbourne, and also Brent McGuinness, who's now with Curtin University. Those three guys were sitting together in the core shed somewhere in Kalgoorlie, that's in WA, in Western Australia. And they noticed a lot of pictures like the one in the middle at the bottom of this slide, so that people don't take too much care of drill core. There's lots of money invested in drilling for exploration, for mining, and but more than often the drill core information is not really preserved, not really properly recorded, and then a company gives up in a certain area, and then the drill core is thrown away. So there's lots of waste of money and lots of waste of time and resources, which is a bit suboptimal. Another issue is also that drill core logging, visual logging, I mean, it's similar to mapping in the field. You know, it's very subjective. It is based on your own education, where you're coming from, your training and so on that you had. It might be depending on the weather conditions also, especially the mapping. But there's very little predictive geological value that can be extracted from these manual drill core logs or from the mapping, let's say. It's very difficult to translate it into something you can actually use for a 3D model or for some machine learning, let's say, in the end. And yeah, the other issue also is that in the resources sector, there are not many cases where information that was acquired during the exploration drilling, that this information is also used later to build the mine. So that's a bit unfortunate, of course. So there's lots of information loss, repeated logging, and to change that, John, Lou, and Brent basically thought about, okay, how about we just develop an automated objective logging of technology, and we develop a technology for automated objective logging of every type of drill sample, so drill core, coarse reject, pulp samples at minimal sample preparation. But it's not only about collecting those data and then just forgetting about them and putting them on external hard drive somewhere, but to make that actually available, for example, via an online portal, via the web. The benefits are clear. This would add immense value to historical investments in core sheds, in cores that are stored at different drill core libraries and so on. And as a side effect, it would also empower geologists with objective geoscience data, especially mineralogy. Okay, so this was about 15 years ago, and that's where we're at now. So this natural virtual core library became reality. And it's you can subset it maybe in these different components that are there in these colorful arrows at the top of the slide. And it starts, of course, with the material, with the sample material, with the drill core in that case, that is either stored at the different drill core libraries from the geological surveys or company drill cores that they are scanning. Then the technology, CSIRO has developed a hyperspectral drill core scanner. We will hear more a little bit about that later on. And this is a picture of the high logger located at the NVCL node in New South Wales. And they're not only collecting high logger data, but also XRD and other geoscience data to get a better understanding about what's in the drill core. As part of the National Virtual Core Library, we're looking after these machines partly. We are also trying to, let's say, make the workflow a bit faster. But we're also looking at how we interpret these data that we are collecting. So the high logger collects hyperspectral reflectance spectra covering the visible near-infrared, shortwave infrared, and thermal infrared wavelength ranges. And I explain later what these things all mean. But it collects lots of squiggly lines, let's say, that need to be interpreted. And we are collecting thousands, hundreds of thousands of data. And so we're looking for some methods where we can very quickly, cost-effectively interpret those reflectance spectra. For that one, we need spectral reference libraries. So that's what's indicated there at the top of the slide. And we also do lots of case studies, like indicated on the bottom right. And then we put all this stuff on the portal. So make it easily available accessible for anyone who's interested. And so this is just a map of Australia, and each of these red dots is basically one drill core that has been high logged, and we've got more than 3,500 now across Australia. But it's a huge database of spectral and therefore mineralogical data. And we're doing, as part of the NVCL, also lots of training, because reflectance spectroscopy is maybe not the most prominent topic And you don't hear that much of it when you study geoscience. Maybe you came across it with remote sensing. If you look at Landsat maybe, or ASTER data even, that's in the end just reflectance spectroscopy, just from space. But not many people get into contact with field instruments or drill core sensors and so on. Usually you learn that only when you join CSIRO or when you join the geological survey or industry. Unfortunately, that's not really taught in universities that much. Okay, so all these components are the National Virtual Core Library, and that looks like a big project, and it is. There are lots of different people involved, and this is just a little screenshot of one of our annual meetings with all the people involved, and at the bottom some logos from the different organizations that are involved. So all the Australian geological surveys, but also on the bottom universities, and on the bottom right highlighted CoreScan, which is a company where CSIRO has commercialized this hyperspectral drill core scanner, the HiLogger, with, and they're developing now the next iteration of this HiLogger. So it's a collaborative project between research organizations and universities and geological surveys and industry. Okay, and so we've got 6 main NVCL nodes across Australia, and you see here pictures of the different setups of the HiLoggers, the hyperspectral drill core scanners in the different NVCL nodes. And so they all have slightly different setups, but it's in the end always the same machine, and they are usually located in air-conditioned rooms, so we can control a little bit better the atmospheric conditions and so on. And yeah, as I said before, we've got now the picture there is quite old in the middle of Australia, but we've got now more than 3,500 drill cores scanned from across various geological environments across Australia. Yeah, and these are the kind of products, let's say, that we deliver or that you can access via the portal also. What we are doing with the HiLogger is mainly collecting the reflectance spectra in the visible, near, shortwave, and thermal infrared wavelength ranges, but also high-resolution RGB imagery, and also a line profilometer. So you can track basically the morphology, let's say, of the drill core. And the plot that is shown here, that was put together by Jess, actually, we see downhole on the x-axis, and you see at the top there a little bar indicating different lithologies, and then pictures of the drill cores corresponding to the lithologies, just representative images. And then you see 2 colorful plots. One is called TIR, the other one SWIR, so thermal infrared and shortwave infrared. And the different colors correspond to different minerals. Yeah? And in this case, we use an automated unmixing methodology where the spectral assistant, this is the method basically, the algorithm, the spectral assistant compares the measured spectra with a spectral reference library and then tries to match those, and then tries to suggest, okay, do we have quartz, mica, chloride, or whatever in the drill core. And the thermal infrared plot, the colors in pink, for example, show quartz abundance, green would be chloride, yellow would be white mica. And the shortwave infrared plot at the bottom shows lots of chloride, lots of white mica, doesn't show any quartz. And the simple reason is that quartz is only active in the thermal infrared, not in the shortwave infrared. Yeah, but again, I will explain this in more detail in the background presentation. But the thing is, different wavelength regions give you different minerals. Yeah, that's the rule basically. Okay, then there's the portal, of course, and Jessica will show this in more detail. The link is a little bit small. I should have copied that a bit larger, but if you type into Google AuScope Discovery Portal, that's the first thing you should get. And it's basically here in the All Layers Borehole section. That's where the National Virtual Core Library is. On the left-hand side here in this downpull menu, and if you add layer, then you should be presented with all these red dots. And it works on a mobile phone. It's a little small, but it still works, and it works on tablets as well. Mozilla and or Firefox and Chrome are the preferred browsers, let's say. Doesn't work too well on Edge or Internet Explorer. Good. I had highlighted. Yeah. So, I mean, Jessica will show that as well. I'm not explaining it into detail, but it's quite interactive, the portal. So we're going to see that soon. The other thing that you could do, apart from accessing the data, you can also do some analytics. I mean, imagine you would have the mineralogy of the whole continent at your fingertip, at your mouse click. Yeah, and that's in the end what we have here. So we are building this in a moment. The search functionalities, the data analytics. We are trying to set that up in a moment and doing some tests. But basically, we have algorithms in there in the analytics part where you could basically search for, let's say, give me all the well-ordered cardinite across the continent in the upper 5 meters of every drill core. So you can ask quite specific mineralogical questions. So if you're interested in phosphates, I recently looked at that, looking just at apatite, because I was interested in apatite, thermal infrared absorption features. You can query the apatites, where they are in the whole database of the NVCL. And then the resulting map would show you where you get the highest abundance of apatite, or potentially apatite. And then you can basically send an email to the respective geological survey and can say, I would like to have a sample from this drill core at this depth because I want to do some analysis, some isotope analysis on some kind of mineral. Yeah, so it's quite amazing what we could do in theory with this portal. Yeah, these are just some screenshots of this data analytics. There's also a report about this. If anyone is interested in this field, I can forward the report. It's public. That explains a little bit the different steps on how to investigate, how to interrogate the National Geological Core Library. Good. The portal is not really part of the NVCL. The NVCL is actually, I should have said at the beginning, is part of the is an AuScope infrastructure program. It's Australian taxpayer funded. And another infrastructure program of AuScope is AuScope's virtual research environment. And these are the people that basically keep that portal going and working. So in the portal, you can access the NVCL data, but also ASTA mineral maps. And that's what I'm displaying here on the right-hand side in this. That's just the one of the ASTA mineral maps. And you can also upload hydrogeochemistry, some geophysical data, and various geoscience data. But you can access NVCL data through a number of different portals, which are pointed out here on the left-hand side of this slide. But the AuScope Discovery Portal will probably be the first one to try. Good, and case studies. So with all these data we really just started maybe doing case studies, and we need many, many more. So we've collected all these drill cores from all these different geological environments, and there was a special issue in the Australian Journal of Earth Science in 2016, which was focused on the National Geological Core Library and what you can do with hyperspectral drill core data. But there's much more. So if anyone is interested in doing honors, master's, PhD, give Jessica or me a call or send an email, and we've got some material here to work on. Good. Other ways how to get involved. We've got a LinkedIn group, which is called National Geological Core Library and NVCL. We're doing lots of training workshops, and we used to do these training workshops in person, preferably, of course. But that's a bit tricky nowadays, so we try to shift that to do it more online. And Jessica is really steering that, and I think we're getting quite a routine now with the online workshops. Just last week we had another one with for the South Australian Geological Survey. Other resources. If you are interested in the high-logger data or in processing them in the Spectral Geologist software, that's also developed by CSIRO. There are some training videos on YouTube. There is a CSIRO Spectral Reference Library that we are also working on in the moment. So there's the big USGS Spectral Reference Library, but we're also developing a separate one with more and more validated minerals in it. And yeah, case studies and publications. Okay, so the National Geological Core Library, what we're trying to do is basically we're trying to provide a friendly online access to this vast resource of drill core mineralogical information from the upper 1 to 2 kilometer of Australia's crust to help transforming the research and applied science landscape. And it is, I think the NVCL is the world's largest drill core mineralogical database. And there are increasing numbers of also international geological surveys interested in setting up virtual core libraries in their countries. So CSIRO has been in conversation with a number of countries to set up something similar in different areas, also in Europe. Actually, I was talking to some people there. And yeah, it has a real impact also for Australian economy. We always, of course, need to justify why we're actually doing this research and these developments. And there was some summary in Radio National here in Australia where they basically calculated that the activity like AuScope, the AuScope infrastructure program, where NVCL is part of, would generate around $16 for every dollar spent on it. So that's quite a good turnaround. And we are quite happy with that, but we want to enlarge that still. Good. I might then hand over to Jessica to show us interactively the portal.
Excellent. Thanks. So I'm going to walk through a bit of an introduction to the Discovery Portal, but I should have done this before we got going. So before I get into it, I'd like to first acknowledge the Whadjuk people of the Noongar Nation as the traditional owners of the land that I'm on today, and pay respect to their elders past, present, and emerging. And so the reason I've got this little critter here is because I'm coming to you all from Fremantle on the West Australian coast. And Fremantle is actually a place in the Noongar tradition is called Wallyup, which is the place of the Walyo, a small kangaroo rat, which is this little guy here. So I thought I'd share that bit of history with you. And then secondly, I also wanted to share something that's an important part of CSIRO and what we do, and that is our commitment to diversity and inclusion. So this is a slide we put together in our program to just kind of highlight how that is something that we hold is important and how it actually drives the innovation and the important work that we do. And I think that extends also to the NVCL, where you can see from this photo that we have a huge cohort of people from all different backgrounds, expertise, states, industries that bring this project together to create the world's largest mineralogical core library database. So with that, we'll get onto it. So Karsten's covered a bit of this already, the different ways you can access the high-library datasets. So through the AuScope portal, the AusGen portal, which is a Geoscience Australia portal. And then every one of the state surveys has their own portal. And so I'm gonna walk you through the AuScope Discovery Portal, which is our main way. And I'm gonna try and do this live. Can you see my internet screen? No, not at all. Okay, I'll try this again. How about now? Cool. All right, so first I will start with what Karsten showed you, the NVCL YouTube page. So if you are keen on how to view the data, you've forgotten what I've showed you today, you can go here and there's a YouTube video that shows you how to access the database and how to download data from it. So it walks you through step by step. There's also a video here which walks you through, once you've downloaded your data from the portal, how do you open it and view it in TSG. So really great resources. So we'll try it from the beginning. And if it doesn't work, you can see I've got about 10 tabs open. And so we'll cheat and go through it that way. So when you go to the AuScope portal, just Google it, click the first link, it'll take you here. And on the left, you've got a series of different layers that Karsten mentioned. You want to look in boreholes under National Virtual Core Library. And from there, you'll be able to select multiple different things. You can select filters. So you can filter by the provider, so which state you're looking for, by the drill date. If you know the drill hole you're looking for, you can search it up. If you want to look in a specific area, you can draw a polygon. I'm going to pick provider because it's not all the states always kind of work as well as you'd like all at the same time. Sometimes the portal slows up a bit. So I'm going to go into Queensland, and I'm glad Karsten showed you that Ernest Henry hole because that's where we're headed. So if you zoom into the state, it's basically like Google Maps. You zoom into your area of interest, and I'm going to take you straight to Cloncurry if I can. So like Karsten mentioned, this is one of the most geologically complex parts of the crust. It's got a crazy kind of deformation and metamorphism history and a lot of world-class ore deposits. And so you can see as I zoom in, all the drill holes in the library have the little names on them. You probably recognize some of these. You've got Cannington, which is a lead zinc deposit, Eloise, Ernest Henry. These are all pretty exciting ore deposits. So I'm going to go straight into Ernest Henry, where we have quite a lot of data. And I've actually been working on a project in that area for the last year or so. So I'm quite familiar with that data set. And I think it's really interesting because Ernest Henry in particular, the Geological Survey of Queensland has been working for some time on this Northwest Minerals province. And so we have about 10 drill holes that have been high logged and go right through the guts of Ernest Henry. And you can see the portal slowed up on me again. So I'm going to skip forward a couple tabs. And so once it's finished rendering, this is what you'll see. You can see this is the Ernest Henry open pit and several drill holes that go right across the guts of the system, and also some distal holes. So if you are interested, there will be a case study coming out on this, which looks at some of that alteration halo around the deposit. And we've done quite a lot of work looking at how, when you go from kilometers away into the guts, how you see changes in the hyperspectral mineralogy and geochemistry and stuff. But for now, we're going to go right into the guts of the system, to this drill hole, if it works, which is one of my favorites. It's called EH550. And so when you click on one of the boreholes, the first thing that'll come up is the drill hole information. So who drilled it, when it was drilled, that kind of metadata. Then if you click on analytic, you'll get the entire kind of drill core photography. And so you can scroll down from the top all the way to the bottom of the drill hole. This is quite a long one. It's about 800 meters, if I recall correctly. But you've got core photography for the entire drill hole. And if you're keen, you can click on it and get it at higher resolution. Ah, it worked. All right. So you have the higher resolution drill core photos, and you can scroll through these. And these are really great because they're taken by the high logger system. So they're all taken at the same parameters. So like the same lighting, everything. So you've got these really nice, consistent drill core photos, and the core is cleaned before it goes through. You'll notice this core is pretty crusty, and that's because it's old. And sometimes that happens, but it's still, it has been cleaned to the best of, as well as you can clean something that's full of sulfides and has been sitting out for a while in the Queensland air. So I think it's pretty good. And so you can scroll through the core imagery, which even without looking at the hyperspectral mineralogy is kind of amazing having all this core imagery. Oops. And then if you get straight into the spectral nerdy stuff, you can click on it and it'll show you a spectrum. So this is showing you the shortwave infrared spectrum for that area, which looks uninspiring. But we'll skip into the more exciting bits. Here we are. So we looked at the core imagery here. You can also plot up some of the mineralogy straight with the core imagery. And so I'll just show you, for instance, see if it works. It'll take a second to render, but what I'm plotting up right now is the Group 1 U TSAT. These acronyms are a mess, I know, but this is the TSA, which is a automated algorithm in TSG that gives you hyperspectral mineralogy for that sample. So this is the #1 mineral group from the thermal infrared that is identified. And so I'll show a legend quickly so you know what I'm talking about. You've got the key things I want you to notice are the K feldspar, which is in orange, and the plagioclase, which is in this pinky color, and then let's say the chlorites, which are in green. So you start at the top of the hole, you've got quite a lot of plagioclase. As you go further down, you start getting more K feldspar and a bit of carbonate and all these sulfates, which is this greeny, gross looking stuff, and more K feldspar. And so you're looking at an IOCG system. So as you get into the real guts of this, you've got quite a K feldspar rich ground mass. And so what you're seeing here is the guts of the ore system. And the reason you see all these sulfates is because it's crusty old core and the sulfides have weathered on the surface. And so if you're seeing sulfates like that, you may be looking at a sulfide rich section. And so it gives you kind of a macro view of the drill hole. The other way to view that is if you go to the scalar tab, you can decide what you want to plot up. I'll plot up the group 1 UTSAS, which is the SWIR, shortwave infrared TSA kind of first mineral group that comes up, and also the thermal. If you plot them up, then you'll get a downhole plot, which is another useful way to visualize this data for a geologist anyhow. I feel like it looks a lot like a downhole log. Fingers crossed it loads. That could be because I've got like 10 web pages open. Or we can skip straight to it, which is this one here. There we go. So when you do that downhole plot, what you'll get is something that looks like this. So you've got the top of the hole, just about 180 meters down to about 1,000 meters. And you can see the distribution of the shortwave infrared active minerals in this one. So the amphiboles in the pink, carbonates in the blue. And you can see kind of this high carbonate area as you start going into the bottom half of the hole in the SWIR. Then as you go into the thermal, you get the minerals that are active in thermal infrared. So this is the silicates and carbonates. And Karsten's going to talk about all this theory stuff later on. But I just think this is a really interesting idea, a really interesting hole to look at, because you can see the change from when you're going, say, more proximal straight into the guts of the ore body. And if you're looking at copper grade, it's low here, and then it spikes right as you get down into this K feldspar and sulfate rich zone. So even by looking at just this kind of raw outputs, you can see something interesting about the mineral zonation in this ore body. And then if you're real keen, you want to see more, you can download the dataset. So go to the download tab, plop in your email address, and it'll prepare the TSG dataset and send it to you. And then you can view it on your own using the TSG viewer. So the other thing Karsten mentioned is the data analytics portion, which is if you are back here on the left menu and you click analytic, you can fill in the relevant metadata, and then you can, for instance, search for a specific algorithm if you want to look at, I don't know, thermal infrared group between 200 meters and 400 meters, whatever you want classification. If you want to look at where you find epidotes at 300 meters depth across Australia, everywhere you can do that. So there's a lot of things you can do playing around with this. And then you can also check the status of your, I don't have any things in progress. So that's a really interesting kind of thing you can do to start looking into the data set as a larger whole rather than drill hole by drill hole. So I think I've covered the most important aspects of the portal.
Okay. So I hope you can see the slides. Good. Okay, hyperspectral mineralogy from drill core to space. I've got half an hour now for this topic, which I could probably talk a whole day about, or 2 days. But let's give it a go. So I thought I'd start maybe a little bit different to usual, because firstly, I wanted to maybe explain why mineralogy. Why are we interested, before explaining hyperspectral and reflectance spectroscopy, why do we care? Why are we interested in mineralogy actually? And I digged out this old picture here on the right-hand side, which is from my master's thesis from the year of 2000, where I did some microprobe analysis of garnets. And in that case, I took those samples from the Eastern Alps, from the Gurktal thrust complex in the Eastern Alps, to understand how basically this whole NAP system they had developed, and how the metamorphism developed, and what's the correlation between different metamorphic events and structural events. And I looked at the garnets to understand changes in the PT, in the pressure and temperature conditions, basically. And for that one, you can use garnet biotite geobarothermometry. And the pictures, the colorful pictures on the right-hand side show on the bottom right, this is the manganese map. And it's quite nice that a garnet, basically, when it starts to grow, to nucleate, it sucks up all the manganese from the environment. Yeah. So if the manganese is if there's any manganese in the rock, it's on large and doing metamorphism, it gets sucked up by the garnets until it's gone, basically. And Other elements, as you see here, top left is iron, top right is magnesium, bottom left is calcium. Other elements get incorporated at different times. Yeah, so we can use mineralogy and mineral chemistry to understand the evolution of geological environments. Yeah, and understanding natural processes. We can use mineralogy for petrogenesis. So basically, yeah, understanding how these rocks formed, under which conditions, and so on, but also for ore genesis. So trying to understand how ore deposits form. And I'm going to show later a few examples of, again, garnets, but at that time this time from a skarn deposit in Peru, where actually the garnet chemistry is really important for ore body characterization, but also understanding at which stage actually the sulfides, the copper-bearing sulfides are forming in the deposit. Otherwise, minerals can also be a bad thing, certain minerals. So in terms of penalty minerals, we want to understand in iron ore deposits, for example, where the clays are, because we don't want to process those clays. So again, mineralogy is really important. And also the economic viability of an ore deposit can be estimated better, evaluated better when we not only look for geochemistry, but also mineralogy. There's the example of the lithium deposits, and I'm going to show later something about green bushes. But basically, in the case of lithium deposits, pegmatite-hosted lithium deposits, it's very important to understand if lithium is sitting in a spodumene, which is a pyroxene, or if it's sitting in a mica, in a muscovite or a lepidolite, because we can process spodumene very easily, but we don't like muscovite or lepidolite for processing. So mineralogy is quite important. And all these different disciplines of mineralogy are quite important: crystallography, mineral chemistry, and also physical mineralogy. So grain sizes differences and all these things are also very important. And these are all parameters we can actually extract from reflectance spectroscopic data. There are also quite some challenges with mineralogy, and maybe I should use this example of the Mount Isa inlier again. It's good and well if you take 10 or 100 samples even, or 500 samples, and do thin sections out of these ones, and trying to map out chemical variations of different minerals in there. It's still just a snapshot. You don't really have a complete overview of all the, or you don't see any gradients, for example. And that's something we often see in the hyperspectral data very nicely. You can see changes, smooth changes in chloride chemistry or white mica chemistry over hundreds of meters. They are changing and so on. So just taking 100 samples and put them on the microprobe is very important to do the ultimate validation, but doesn't give you the whole picture. There's also limitations to what the human eye can identify simply. And I'll show that on the next slide, what I mean with that. The human interpretation is also very subjective again and biased. No, it depends where you're coming from. Where did you do your first ore microscopy or thin section microscopy course, or just simply drill core logging exercises? Can be very biased. So a pyroxene can be an epidot, or can be a chromite, or any of those sometimes. Then finally, translation of this human description into information that actually can be used for like a 3D model or for machine learning is also very difficult. If we receive lots of information from companies about with the drill core logs, and then they have their alteration indices, and that's all firstly handwritten, but then typed into Excel. And then there are some really weird classifications of alteration and so on that are not really that helpful. They're either too specific or too general. So we're trying also to use hyperspectral data to maybe develop some parameters, alteration indices or something that can be objectively extracted from the data, from the squiggly lines in this case, simply, yeah, without too much interaction from geologists at first place. Good. So going back to this point about limitations to what the human eye can identify. So on that slide, you see some pieces of drill core from the Yilgarn craton somewhere from a greenstone belt. Different shades of gray and green, interrupted by some carbonate veins, potentially. At the top, you've got like a pinkish vein that is cut in a weird way in this case. And that's all nice and well. If you look in, so that all looks very similar. No? They're all very fine-grained rocks, and you need a hand lens to maybe see some amphiboles if you can, but it's going to be really hard. And we're not even starting to talk about amphibole chemistry with a hand lens. So, and on the left-hand side in this diagram, you see the reflectance spectrum, and I highlighted just the visible part of the spectrum. Yeah, so our eyes can see roughly between 380 nanometers and 700-ish nanometers from blue to red, basically. And you see that the reflectance profiles, maybe I can show my mouse, actually, that would be good. Yeah, so you see in the reflectance profiles, they all have roughly the same shape, yeah? We see it's very suppressed here in the violet to blue part, and in the higher in the greenish part, so the rocks are really green, it's true. And then it decreases again towards the red. And they have all roughly the same shape, apart from the one at the top here with this vein, where we have lots of red. And this explains basically high reflectance, red color. That's basically like this pinkish bright color here that we see here. But they look all very similar. So if we now extend the wavelength range, we can look at, if we could now just imagine our eyes would be able to capture a larger wavelength range, and we could look into the infrared. That's what we would see. So we see much more detail to this reflectance spectra now. Yeah, much more information. We see basically more colors. And you see that at the top, we have these absorption features that we see here, these troughs in this case. They tell us that there's some epidote and calcite here at the top in this vein. This rock here in number 2 is dominated by chlorite, the next one by amphibole, and so forth. And it all comes down to some really small but diagnostic differences in these reflectance spectra, especially here around 2,300, 2,400 nanometers. Yeah, so the presence or absence of the respective absorption feature will tell me something about what kind of mineral is sitting in here, in this rock. So we're actually not using the color, but which is the part that is reflected to us. We're using actually the part that is absorbed, because the absorption is due to a certain molecule or a certain element that causes the absorption. Yeah. So you've got different processes. You've got electronic vibrations and molecular vibrations. The electronic vibrations, like for example iron, charge transfer in iron, for example, will cause these absorptions here in the epidote. So these are ferric and ferrous iron absorptions in epidote. These electronic transitions mainly happening in the visible near-infrared part of the spectrum, and in the shortwave infrared part of the spectrum, we've got these vibrational modes, which are due to certain molecules. And namely, in that case, with epidote and with chloride and amphibole, these absorptions are related to hydroxyl groups. Yeah, so OH groups, and then we've got the OH bond, and that starts vibrating, and the vibration is absorbing energy at a certain frequency, and it depends then what kind of cation is bonded to this OH bond, and that will trigger basically where the absorption occurs. Yeah? So because we have different cation environments here in chloride and amphibole, that's why these absorption features shift or are located at different positions. Okay, so this is actually all you need to know in terms of reflectance spectroscopy. If you understand that, then you know everything. It's very simple. So we can now assign those different absorption features. We know quite a lot about the visible near and short infrared. There are other wavelength regions where we don't know that much. We are learning still, but we basically can assign these different absorption bands with certain transition elements or with certain molecules here. And these are just some abbreviations. That's how we give, these are the names, let's say, of these absorption features. Okay. But why do we do that? Why do we do this analysis? Okay, we want to understand mineralogy. That's nice and well, but it actually has also, let's say, applications for the resources sector. And here's an example on the left-hand side of an epithermal system after Tostal 2009. And we've got our classic hydrothermal breccia here in the middle, which contains basically all the ore, the sulfides and so on. And this is surrounded by a quartz alunite alteration halo. proximal to the mineralization. And then if we're moving outwards more distally, we are going through these other alteration mineral assemblages. So from this quartz alunite alteration, we're entering the clay alteration, the kaolinite, dikite alteration, and we got some sulfates here as well, alunite still. Then we're going into clay and sericite alteration, and we end up in propylitic alteration, then further outwards into these green rocks, which are full of chloride and epidote, more so in porphyry systems then. And so there are certain indicator minerals that tell us where we are in this alteration system. And we are very lucky that in nature, in the shortwave infrared, most of these alteration minerals that we care about do actually have distinct absorption spectral signatures. Yeah, so you can nicely distinguish the alunite from carinite, from the poorly ordered carolinite like a halloysite, from smectites represented here by montmorillonite, then illite representing the white micas, chloride and epidote. And we can basically walk from proximal to distal from the system. So if you take two samples, let's say at a minimum, I guess, and one sample shows you an epidote signature, the other one sample shows you carinite, well, then you have to walk in this direction basically. And then in theory, at least according to the model, you walk towards the ore. This is now the example of an epithermal system and porphyry system, but there are a number of other examples for VHMS, so volcanic hosted massive sulfides systems, but also Mississippi Valley type, scans, IOCGs. They all have their certain indicator minerals, vector minerals towards the ore, and you can apply the same principle basically. Yeah. And it's very commonly used also, reflectance spectroscopy, for that purpose, identifying different minerals, especially here in the shortwave infrared part of the reflectance spectrum. So we're looking at the wavelength range between 1,300 and 2,500 nanometers. This is the wavelength range you can typically collect with a field spectrometer like the TerraSpec or FieldSpec or the Ore Express. These are the kind of instruments that are commonly used. And this is also a wavelength range that is easily accessible with airborne sensors like HIMAP or SpecIM's Phoenix system, ITRUS, their head wall. There are multiple systems around, and also drones nowadays also can collect parts of this spectrum at least. Yeah, what we are working on more now also is understanding better compositional changes of these different minerals, because there's more to the story than simply changes in mineral assemblage. There's also, it's important to track the mineral chemistry. Okay, but before I talk about that one a little bit more, this is just another overview I want to give now about the different spectral sensing technologies. And we're looking now at a wider, broader part of the reflectance spectrum. Yeah. So I've got here 4 minerals from top to bottom: carinite, then quartz, goethite, and hematite. And we're looking here on at the wavelength range from about 350 nanometer up to 16,000 nanometers. Yeah. So ways beyond the shortwave infrared. We are basically crossing the midwave infrared and entering the thermal infrared. Other countries, areas call this wavelength range here the far infrared or the long wave infrared. I would recommend just look at the numbers, just look at the nanometers, and then you know where you are. Don't focus too much on if it's MIR, TIR, or FIR or something like this. The important point is here that basically different wavelength ranges enable you to characterize different minerals. The visible near shortwave infrared is, as I showed before, good to identify any mineral that contains hydroxyls. So in geologists' language, that basically is white micas, chlorides, amphibole, epidote, and all the other clay minerals, but also sulfates like jarosite and alunite contain hydroxyls. Anything that contains hydroxyls will absorb in the shortwave infrared. So therefore, the carinite has strong absorptions here. But it has even stronger absorptions in the midwave infrared. I left this part still gray. It's an old slide, slightly older slide, but I left it still gray because this is a wavelength range that is not really easily accessible for many people. Especially if they're using remote sensing, then this is almost a no-go zone. But there are instruments, field sensors around where you can access this wavelength range. But in general, if you're interested in carolinites or chlorides or white micas, Short-wave infrared is usually good enough. And then there's some more information about thermal in the thermal infrared, again, from these hydroxylated sheet silicates. If you're interested in quartz, then you need the thermal infrared mainly, because quartz doesn't contain any hydroxyls, at least nominally it doesn't contain any hydroxyls. Therefore, you will not see any absorptions in the short-wave infrared. Yeah. So if you're working in the scan system, for example, where you don't have that many short-wave infrared active minerals, you need thermal infrared basically. With iron oxides, the visible near infrared is really important because they are full of iron. So you got all these the absorption features related to iron here, ferric iron charge transfer and crystal field absorptions. There are also absorption features here in the longer wavelengths in the far infrared, but it's really difficult in natural samples to make sense out of these things. We're doing lots of comparisons with natural samples like collected with the NVCL, comparing those ones with single crystals and literature about single crystals, and it's just a different world. Yeah, you can nicely identify or discriminate different goethite and hematite species or ilmenite in the far infrared, but in a natural sample, good luck. Okay. Let's have a look at different technologies that are commercially available. So I just overlaid that here, these reflectance spectra of the different of these 4 different minerals. So field spectrometers you maybe had a chance to use already, or you heard of the TerraSpec and FieldSpec from Malvern Panalytical, or Spectral Evolutions field spectrometers. They mainly cover visible near short-wave infrared. There is a handheld spectrometer from Agilent, and handheld FTIR that covers the whole mid-wave thermal and even into the far infrared, yeah, which is a pretty cool tool that we are using quite a lot now, especially for lithium. The HiLogger 3, that is part of the Natural Vector Core Library, collects visible near shortwave and thermal infrared reflectance spectra. There will be, hopefully soon, by the end of June next year, a HiLogger 4 that also collects mid-wave infrared reflectance spectra. Then there are other drill core scanners. So I should say also, I didn't mention it before, the HiLogger is a line profilometer, yeah? It collects basically in a stepwise function, every half centimeter roughly, one spectrum. So it's not creating an image, it's just collecting points. But there are a number of different imaging spectrometers, and I believe also there's, in Britain, you have access to these ones. Imaging spectrometers where you create basically an image of your drill core, of maybe the center 4-3 centimeters of your drill core at a very high spatial resolution. So that would be then like in the half millimeter resolution, maybe per pixel size. So typical instruments are the hyperspectral core imager 4 here, also developed by CoreScan, then SpecIm's Phoenix system, HiSpecs, Headwall, and there are a number of other providers of this system. They are mainly focused on the visible near short-wave infrared. There is one system, SpecIm's OWL system, that collects also long-wave infrared. So there's an imaging system, drill core imaging system, that you can use to detect quartz, pyroxene, garnet, and so on. And the interesting thing is that SpecIm's Phoenix and HiSpec system, you can use almost the same machine and mount it into a helicopter or an airplane, and you can do then a remote sensing. You can also simply turn it sideways and look at the mine phase image. Mine phase basically created a hyperspectral mineralogical map of your mine phase. And there are a number of case studies. There's a nice one by Kai Yang done on Konyambo, nickel laterite deposit in New Caledonia, where he mapped the ore-bearing minerals, and also in the end he predicted the nickel content. He put that on the image, basically, on the mine phase image. Since maybe a few years, 3-4 years now, companies are more and more playing around also with conveyor belt scanners. So there are some instruments like the Quality Spec or SpecIm's FX50 that are basically attached to conveyor belts in a mine, and they basically scan what's traveling on the conveyor belt underneath and try to identify, like BHP iron ore, for example, is using the system to identify kaolin content, iron oxide type, and moisture content. because these 3 parameters are very important for them to understand if they can process the ore or not. Because if it's too wet, if there's too much moisture, then it clogs up the processing plant and they can shut down the mill for a day, which costs them like several $1 million. So the spectral sensing technologies can be used at various scales with various instruments. But if you want to get into it, think about first what you actually want to get out of it. Yeah, think about what's your application, what's your question. I've seen a number of cases where people think, hyperspectral sensor with a drone, awesome. Most hyperspectral sensors that you can attach to a drone only collect a certain part of the visible near-infrared, nothing else, which might be very good for mapping rare earths and iron oxides and so on. But if you're interested in garnet, for example, then it's useless. So really, you need to understand which wavelength region is important and for you to address your questions. And a number of papers around that summarize it actually nowadays. Okay, with the drill core reflectance spectroscopy, it's not only drill core that you can analyze, you can also scan chips, you can different sizes of chips, you can analyze pulps, and we've generated a number of different holders so that we can scan reflectance spectra from these different materials with a high logger, for example. Our colleague Ian Lau, he's the expert in these kind of things. Yeah, so this is mainly what I wanted to show here with this slide. Maybe just here on the bottom left again, this is roughly a sampling area. I should have put maybe a scale of the drill core, but it's a vertical view of the drill core. So you see the width of the drill core on the x-axis. Maybe that's 5-6 centimeters here from left to right. And then you see roughly the area that is collected with the high logger. Very roughly. Yeah. Good. And so this slide just shows a snapshot of what's available. There are lots of proximal sensors, like the field spectrometers, like a high logger. There are a number of airborne sensors also. And there are also satellite systems. And we are quite lucky now, actually, for remote sensing. 2020 was actually an excellent year, I have to say, because we got access to lots of data from hyperspectral satellite called Prisma, and NMAP is hopefully being launched as well soon. And there's also DSIS. So there are a number of spaceborne systems now that enable us to get hyperspectral resolution imagery from the Earth's surface. It's quite exciting days. The pictures here, this like on the bottom right, this cartoon of the Aster satellite system. It's a multispectral satellite. In the middle here, this is a picture of HIMAPS, visible near short wave infrared sensor, and they also have a high resolution QuickBird camera in there. Top right here is again a picture of the high logger. And I might just say, I forgot to say that before. Basically, you're putting the drill core tray or your other samples on this table here. The table then moves in a snake-like fashion underneath the spectrometers, which are hanging down from this crane here. And that's how you collect the data. It takes maybe like 5 minutes to collect reflectance spectra from one drill core. Yeah, and then we've got field spectrometers like the TerraSpec, and this one here in the middle, this is the handheld FTIR from Agilent. Okay. Good. There are multiple hyperspectral sensing applications, not only characterizing mineralogy, but also, well, mineralogy equals, in the end, mineral assemblage equals lithology in the end. So you can characterize lithologies, you can identify duration minerals. Sometimes you can map the ore directly. Many people ask us, can we map sulfides? No. I would say simply you can to a certain degree, but reflectance spectroscopy is not the right method to identify different sulfide types. It's not what it's made for, I guess. But you can map iron ore, you can map copper chlorides, which you find in porphyries and so on, and other interesting minerals. Or if you're interested in rare earths, you can actually identify differentiate different rare earth elements in the visible near-infrared. You can map planetary minerals, mineral composition, crystallinity. You can get an idea about the water content, the bonding. You can estimate grain size. in terms of mineral content, you only get the relative mineral content or relative mineral abundance, yeah? With reflectance spectroscopy, it's a very complicated process, the reflected light, let's say. Various scattering processes going on, volume scattering versus surface scattering and so forth. You can only estimate. You can maybe say, here's more of white mica than over there, but that's it. If you want to get quantitative mineralogy, then you need to calibrate your data set with an independent measure with, for example, quantitative XRD or QEMScan derived mineralogy. Then you get your quantitative mineralogy. And in the same way, like you train basically your reflectance spectra with those independent measures. You can also train your hyperspectral data set with geochemical data or petrophysics or geometallurgy. And then you can predict these parameters from your hyperspectral data. Okay, I want to show quickly one case study about the garnets, coming back to the garnets, just to show how that's all is applied. So this is from the Antamina skarn-hosted copper zinc moly deposit in Peru. And in this case, we had a porphyry intruded in some sediments. And we've got skarn alteration along the contact of with these sediments, which is cross-cut by later hydrothermal fractures. The main mineralization is copper, zinc, moly, some silver, and some bismuth. The majority of copper zinc is located in the exoskarn, so in the altered carbonates, and the majority of copper moly is located in the endoskarn. Yeah, so there's already a separation of different ore parts of the ore system in the endoskarn versus exoskarn. But when we look at the garnet composition, then it gets more interesting. And we had a closer look. We did some microprobe analysis and infrared microscopy as well on different garnets. And we basically found various grossulars and androgyte, and we went to the very detail here. This is just some backscatter image of this garnet, of this zoned garnet, and the corresponding infrared absorption spectra, reflectance spectra, and we see these absorption features here in different colors, according to the plot on the top right. And we see that these absorption features shift. And the shift of these absorption features is due to different cation environments of the silica tetraheders in this case, silica oxygen tetraheders. So we're replacing aluminium by iron. There's a typo here. And that basically induces the wavelength shift. And we can track the compositional variation of the garnet. And we found that the sulfides mineralization is associated with compositional change of the garnet from grossular to the androgyte. Yeah, so later stage androgyte, and that's when the sulfides are coming in. And this is a very complex plot, or not very complex, but very colorful, lots of dots. And what I've done here is simply I extracted the wavelength position of the garnet absorption features that I showed on a previous slide. On the x-axis, there's a certain absorption feature. The wavelength position of that one versus the y-axis is a different absorption feature, and plotted them against each other, and I colored this up by different sulfides, that information provided by the company. And we can see that the exoskarn here, dominated by pyrites and chalcopyrite, has very, what we would say, maybe long wavelength garnets. So we are ending more with the androgytes. Whereas especially the high moly copper zone has a different composition. The garnets have a different composition. Yeah, so we see the association of different garnet composition with different parts of the ore body, and it hopefully will be published or coming out, released next year in Mineralium Depositor. That's coincidence. Okay, with this slide, I just wanted to show quickly that the reason why we use actually absorption features instead of spectral matching, so people that have used maybe reflectance spectroscopy before, they know that we're using spectral libraries often to match our minerals and so on. But I guess I'm a bigger fan of using looking at the exact absorption features, because they help us. If we're looking at the absorption features directly, we can track the chemistry, mineral chemistry directly, yeah? And that's what we can do here, no matter if we look at drill core reflectance spectra, like here shown on top, or reflectance spectra from coarse reject. So you see those squiggly lines from these different sample materials. They look quite a little bit different. And especially with the fine-grained material, we're introducing this volume scattering here, around 7,000 to 8,000 nanometers here. And that all distracts us from extracting the right minerals. But if we're focusing on the main important absorption features for garnets, we see that they're actually pretty much the same, and they're unaffected by volume scattering. So it doesn't matter if I have coarse reject samples or pulp samples or a drill core, I always get my good garnet spectra. Okay, and you can do the same using airborne. So this is a case study done by Tom Cudahy, which I think is only available in the report, but he used data from Yarrington, Nevada, where in this area we've got actually porphyry, we got epithermal porphyry and skarn systems in one area. It's very complex geology there. But there is this paper by John Dill et al. From 2000, where they used microprobe analysis to identify garnet compositional changes. And they found out that there's a relation between the garnet composition again and the ore deposit, yeah, where we find the ore. And Tom Cudahy used some CBES data, which is a thermal infrared airborne instrument, awesome stuff. Where he basically mapped the iron aluminum ratio in granites in these garnets to track vector towards the ore deposit. Yeah, you can use remote sensing to vector towards the ore deposit, which is quite cool, I think. So, and now I'm in the old dilemma that I'm desperately over time, so I will skip the next 2 slides and might just jump ahead. Yeah, there's another case study, just quickly, done by Heta Lampinen on white micas from the in the Capricorn origin from the Abra lead zinc silver deposit. If you're interested in this, that's the publication. It's in Economic Geology. And if you have questions, you can send us an email. What I could just quickly, if I can steal another 5 minutes, want to draw on is the different spectral resolution of different instruments, because that's quite important. We are very spoiled in the NVCL, and also when you use field spectrometers, so you have this hyperspectral resolution. What's hyperspectral? Hyperspectral is basically lots of bands that are collected. And here I've got an example of a drill core. That's a drill core from New South Wales intersecting a porphyry deposit. And we can see the different reflectance spectra going through the propylitic, phyllic, advanced acylic, and oxidized and advanced acylic alteration. So we're actually, again, from bottom to top, we're going from distal, we're going closer to the ore deposit when we're moving up here in these reflectance spectra. And that's all good. If we resample the spectral resolution to high map resolution or airborne hyperspectral, that's what we're left over with. So it's still quite good. We're losing some information here, some of these details, but it's still okay. We can still make sense of, we can still identify propylitic versus phyllic alteration and so forth. And this one is here something where we just modeled how NMAP would look like, the space-borne hyperspectral satellite that hopefully will still be launched. Should be good as well, if there wouldn't be in the atmosphere. So if you're using remote sensing, you have atmosphere, luckily enough. And that means that wavelength ranges around 1400 and 1900 nanometers are absorbed. Yeah, so that's water vapor mainly, but also other gases. And that's why the good part where we got lots of information around 1400 nanometers you can't use. It's just swamped by atmosphere. That's one challenge with remote sensing. The other challenge is many remote sensing instruments are just multispectral. And in the case of ASTA, that's actually what you're left over with in the shortwave infrared. 5 bands here. So not much you can work with, but it's still actually good enough. You can still distinguish carbonates from, well, yeah, let's say you can distinguish chloride from white mica, from amphibole and so forth. You can still do this with ASTA, even though you have just multispectral resolution, you just have 5 bands here that you're left over with. So which brings us to ASTA just quickly. So we've got here the wavelength range on the x-axis between 400 to 2,500 nanometers, and then we do a little jump and look into the thermal infrared. And highlighted here are the bands that are collected by ASTA. Yeah, so it's a multispectral system. We've got only 9 bands in the whole wavelength range between visible near to short infrared, which is in contrast to hundreds of bands, or close to hundreds of bands in the high logger. And this is where the bands are located, and you've got a few more bands in the thermal infrared also. The reason why these bands are collected there is because that's where our mineral absorption features are. Yeah. So ASTER is what we would call maybe a geoscience-tuned spaceborne system. Yeah. It really is designed to map minerals, which is in contrast to Landsat 8, which is used by many people to distinguish minerals, but actually you can't distinguish minerals with Landsat. Sorry. You can map iron oxides with Landsat. That works quite well because we have this band number 5 collected around 9 nanometers. But there's no way to distinguish chloride from white mica from carolinite or something like this. That just doesn't work. You might, if you apply some clever machine learning approach and then you might be able to do that, but it's a very case-specific application then, yeah? If you use band ratios in ASTER to map out the different minerals, then you can apply that everywhere on the globe, and it should work, actually. Worldview 3, this is also highlighted here in this diagram, which is quite useful. Worldview 3 has roughly the same bands like ASTER. It's missing out on some information here in the short-wave infrared, but it's still quite good, and it has a better spatial resolution. ASTER, in the short-wave infrared, the pixels are 30 meters pixel size. That's quite big. Worldview 3 gets you down to maybe 3.5 meters, I think, which is pretty. Again, ASTER is actually superior then in that case because you can identify quartz. And just quickly here, this is an example of an ASTER mineral map we created from the Australian continent. So about 10 years ago, we started downloading lots of ASTER data from the NASA Globus webpage and so on, around 30,000 scenes. We looked at all these scenes and removed the ones that had too many clouds or not enough data or some instrument issues. We're left over with about 4,000 scenes. And then Mike Cacetta here did the hard work at CSIRO and merging all these scenes and creating a 1 continental scale mosaic. And this is 10 years old already, this image almost, but it's still quite beautiful, I think, and really telling, not only beautiful. This one shows us the relative amount of aluminium-bearing minerals, aluminium OH-bearing minerals. So this is white mica, smectite, and carolinite mainly. And red colors would be lots of that stuff, and blue colors would be not so much. And you see lots of striping here, but we don't care too much about that. We see basically lots of aluminium OH-bearing minerals here in the western part and also here in the center where we have the deserts. And yeah, there are multiple applications of this one. One of them is, for example, Tom Cudahy, who put that together mainly. He did a study about tracking the source of dust storms that impact on Sydney. So the dust is coming from over here, from the west. And other applications, I might skip that one because this one is a nicer application, or the more interesting one maybe. You can use that for mineral mapping and still discover outcrops. Yeah, so we are told by many people that all the deposits at the surface have been discovered already a long time ago. I'm not so sure about that. When you use the ASTER mineral maps, for example, here I've just used 3 of them on the right-hand side. This is an example from the Eastern Arunta Inlier in the Northern Territory. Eastern Arunta Inlier, we expect maybe some IOCG deposits or SEDEX, metamorphosed SEDEX deposits. In any case, the companies are exploring here along that J, basically in the Jervois area, where they have got some copper mineralization hosted by cordierite schist and 2 mica schists. Okay, 2 mica schists. If there are 2 mica schists, the host of the mineralization, then maybe I want to use the aluminium OH group content image to track the mica schists. Yeah, and this is what you see here on the top right image. So the high values mean basically lots of white mica in that case, and blue values are not that much white mica, or no white mica in yet. The bottom image, bottom left one, that's where it gets interesting. The red pixel this is the MgOH group content, so it would tell us about occurrence of chloride and biotite. And we noticed in that area here that there's lots of biotite or chloride alteration just to the southeast of the known mineralized trend. And we showed this to a company during a workshop, and they said, yeah, well, there's nothing. We've been there. We are mainly focused here in that area along that J and in the quartz cordia schists and two mica schists and so on. There's no point in looking at the other area. And I said, okay, good, then not. But they sent actually two colleagues from the company out there in the field. They did some sampling and they found 50 grams per ton gold in quartz veins. Yeah. This is not a deposit. This is not forming now the biggest gold deposits on the planet, but just simply by that we could show that you can use remote sensing data to map alteration minerals that could point you to some quartz veins that contain some gold was a quite nice example. So I really would challenge, I'm very happily challenging everyone who says all deposits at the surface have been found. I don't think so. Good, I'm heavily over time. I'm very sorry about that. I might just skip to the next slide that catches my interest. Yeah, so just quickly, so I talked a little bit about remote sensing, drill core sensing, field spectrometer data. In the end, we want to bring this all together and put that in a 3D model. And I might just highlight here the case study area of Rockclear Dome, which is a channel iron deposit. But even for people that are not really interested in iron ore, this is exciting because you can apply the same concept in all kinds of deposits. What we've done there is we have integrated airborne hyperspectral data with the drill core hyperspectral data and created a 3D mineral map of iron oxides, but also kaolin crystallinity. We looked at the kaolin crystallinity to map transporter versus in situ material. But we also distinguish different kinds of clays, different kind of smectites and so on, even with the airborne and the drill core hyperspectral data. Yeah? The significant part, I guess, from that case study here is for the company was that they drilled lots of drill cores. You can faintly see them here by these vertical strings. And due to the integration, based on the integration of the airborne and drill core hyperspectral data, we found out they could have saved actually 30% of the drilling if they would have first looked at the airborne hyperspectral data. How that was done, I need to refer to the publication because I'm really heavily over time. Okay, so in summary, reflectance spectroscopy provides cost-effective, spatially comprehensive information also about the Earth's surface composition from the mine to the continental scale. Yeah, it's amazing things you can see in these remote sensing images, and even from the Mount Isa layer. It's very important to integrate surface and subsurface data, which could be used then to support the whole mine value chain. But it's of course not only reflectance spectroscopy. If you just look at reflectance spectra, it's also pointless. You need to integrate this with geochemistry, with petrophysics, with other data sets for validation and so on. But reflectance spectroscopy has a wide range of applications, ranging from exploration to the resource characterization, like in Antamina, geotechnology. It has geotechnological applications and also environmental monitoring. There are numerous case studies where people, for example, mapped the acid mine drainage by estimating the pH changes from different jarosite contents and compositions. Yeah, and you can do that with remote sensing data. You can map dust pollution, like on mangrove leaves and so on. So if you look at publications by Cindy Ong, especially Tom Cudahy and Ian Lau, then you find all that is an interesting part. The challenge is that, and that's really the last slide, we probably need a few more geoscience-tuned remote sensing systems. So something that is really designed for mapping the minerals that we care about, that we're interested in. The processing of these reflectance spectra is still quite a mystery to many people. And hopefully I didn't make it more mysterious now, but it's quite challenging. And I guess geologists, mineralogists, and remote sensing people need to work hand in hand, and we need to do more of these kind of workshops and training. There's also lack of understanding of mineral footprints through cover. So with the examples of the propylitic and sericitic alteration and so on, advanced agalic alteration in porphyry systems, this is a model based on not fresh rocks, but altered rocks. But how does it look like through the regolith? That's what I'm interested in. So I want to know does any of these do any of these indicator minerals actually survive the weathering and exist up in the surface or not? And we've done case studies about that. We found that good indicator minerals that are rather weathering resistant are talc, for example. If you're looking for some mafic, ultramafic rocks further down, the talc is quite weathering resistant, so you can find it at the surface. Iron-rich caronite, weird things that survive through at the surface and might tell you something about what's hidden further below. Yeah, and also what we are working on heavily in CSIRO at the moment is understanding relationships between the spectral sensing data and other geoscience data. So what's the relationship between geochemistry, petrophysics, and spectral sensing? Okay, I leave it there, totally over time. Thanks for your attention.
Okay, and I'm just going to now pass over to Jess, who's going to be talking us through the first case study.
All right. Yeah, so today I'm going to walk you all through a case study from WA. And so this is a bit of a greenfield situation. So we thought we'd do one that's in an active mine site and one that's more greenfields. And so I've entitled this case study, Correlating Stratigraphy and Identifying New Mineral Systems in the Fortescue Group. So just an outline. First, I'll go through a bit of the geological context. Then I'll talk about some of the hyperspectral data sets we're working with. Then I'll bring some geochemistry into this because a lot of the NVCL data sets also have geochemistry. And I have a background in geochemistry and hyperspectral, so I like bringing the two together. And I'll use those data sets to talk a little bit about correlating stratigraphy, looking at sediment provenance, looking at alteration in mineral systems, and then a little tidbit about what Carsten is referring to around the PLS modeling, so predicting geochemical parameters from hyperspectral data. So this is a project that is not it's part of a larger project, which is not just NVCL, but we did it with Artemis Resources and the GSWA through the Exploration Incentive Scheme. That's how they did their drilling. So just context. So we're talking about kind of northwestern WA in the area of the Fortescue Group in the West Pilbara superterrane. So this is up here, where some of you may be familiar with this around some of the hype from the gold nuggets that were being found everywhere in the regolith. People were walking around with metal detectors, finding huge nuggets. It was all very exciting. And that there's showings of gold nuggets all over the area, but the kind of western side of Pilbara, West Pilbara superterrane is not really well studied or understood. Most of the work's been done here in the eastern area where you have all these gold showings. And so this work was spurred by some interest in the area because of 2 new gold showings in an area called Purdy's Reward in the 47K patch. And we did some work with Artemis Resources on that. There's a new paper out on that if you're keen on the whole nugget story. But that was 2 showings, and we know that the Fortescue Group extends further south. And so there were some questions around how far south were those gold-bearing terrains. And so just a bit of geological introduction for those of you that are not familiar. So the Fortescue Group is about a 6.5 kilometer thick package of sedimentary and extrusive rocks, and it unconformably overlies the Archean Pilbara Craton. So it's got 4 major stratigraphic units. And several types of mineralization. So the nuggets is the one that's kind of been in the news in the last couple of years, but there's also some minor uranium, copper, base metal, and stuff like that. And like I mentioned, it's kind of poorly correlated in the West. So the main units, you've got the Jarina Formation, this top area here, this middle section here, with the Medina, Tambiana, and Kailina, and then the Hardy and Mount Rowe, which overlie the basement. And so I'm going to talk about a couple drill holes. One is this new one, this old one here, DD84MF1, which intersected a gold nugget here in the Hardy Formation. And then this new drilling, which intersects the top section of the stratigraphy. And just for context, the gold nuggets were found in the bottom of the Mount Rowe basalt in the conglomerates. So they're generally found in these conglomeratic units near the basement contact. And that's where those showings at surface are. And so what kind of spurred this project was Artemis has these holdings up here where you've got gold at the surface, and there's a drill hole down here, which was drilled in 1984 by the CRA. It's a stratigraphic hole, and it hit a gold nugget at about 1,700 meters in this big conglomerate unit. So they're like, all right, how does this vary distally? Can we understand does this unit come closer to surface up here? What's the extent of it? And that was largely driven because this 1984 hole was high logged in 2018, or I think it was around 2018, to better refine the stratigraphic boundaries and rock types. And originally when this hole was drilled, they thought that they might have hit the basement. And so there wasn't clear, did we make it all the way to the basement or not? And upon looking at the old drill core with the high logger data, it became clear they really hadn't. And so that kind of was an interesting little tidbit. And so the company decided to drill a couple other holes. So these two holes here are we're going to be presenting to you mostly, this new drilling. And so here's just the stratigraphic hole. It's about 2.5 kilometers. It's colored in the Medina Formation, which is a volcanic, kind of volcano-sedimentary unit. It goes to the Tumbiana Formation, which is a sedimentary unit, through the Kailina, which is a metavolcanic, and then this thick package of Hardy Formation, which is a metasedimentary unit with these big conglomerates at the base where the gold was found, and it kind of bottoms out in the Mount Roe basalt. And so they missed the actual big gold-bearing conglomerates, which are the base of Mount Roe basalt at the basement contact. But you can see even from, this is the summary screens from the high logger data, that some of the lithological contacts are a bit difficult to visualize. And I'll get into that bit of that later. You can see here, for instance, is not intuitive that the Kailina Formation ends here because you've got still the strong chlorite signature below that. I'm going to go into that a bit later. And also in here where you've got the Mount Roe basalt and the base of the Hardy, it's got similar mineralogical composition, so really chlorite and carbonate rich. And that's largely because this basal conglomerate unit is composed of bits of the underlying unit. So the company wanted to know what's the extent of these gold-bearing lithologies. So they drilled these two drill holes. It was intended to be one really deep hole, but they hit basement at 700 meters and then drilled through another 700 meters of basement because they thought it was an intrusion, which it wasn't. And so we ended up with a second kind of twin hole next to it. Instead of 1 3-kilometer hole, we got 2 holes. And this was to target the basement contact, but also to look at other base metal anomalies. So in the VTEM data, regional VTEM data, there were some base metal anomalies along the Tumbiana Kailina contact, and they wanted to interrogate those. So because these are EIS holes, so they're drilled through the exploration incentive scheme that GSWA runs, they were both high logged. And so this data is in the NVCL portal. And I worked on this as a part of a greater project and have continued that through my NVCL work. So hopefully this is not new at this point. So the high logger gives you basically centimeter scale hyperspectral data from the SWIR and the thermal infrared, and that can be converted to mineralogy. And so if you just look at the hyperspectral outputs from the thermal infrared, which is what I've plotted up here, you can correlate the stratigraphy really well. And you can see kind of the contact between the Tumbiana and the Kailina formations. This is the first hole, and you can see it, I mentioned it intersects a huge section of granite basement. The second hole is shorter, and you can see the contact with the basement really clearly, and it's clear that the first CRA hole really does not hit the basement at all. One of the more interesting bits is that this Hardy Formation section is only about 150 meters thick in the first hole. It's about 200 meters thick in the second, and then, you know, nearly over a kilometer thick in the third hole. So it's telling you something about regional basin architecture. And then there's some other units that are interesting too. So top of the Hardy, you've got this really chlorite rich unit, which you can see in all three. And the Kailina Formation has this characteristic kind of chlorite quartz plagioclase. It's a metavolcanic. And then you've got this really heterogeneous sedimentary unit up top, which still has this section here that's really kind of chlorite rich, which correlates pretty well here. Then you get this carbonate rich stuff through the center. And then the base is a bit harder to correlate. This is without doing any higher level processing, just using the automated outputs from PSG. You can quite clearly correlate the stratigraphy across about 15-kilometer strike in an area where there are no other drill holes. And so in addition to the high logger data for these holes, we worked with some mineralized data, which is continuous XRF. So this gives you kind of centimeter scale measurements, which you then bin to generally a meter to improve your sampling statistics, but you get continuous geochemistry down your drill hole. So it created kind of a unique situation to look at the two data sets together because they're collected at the same scale. And so I mentioned that top Tumbiana unit is a bit heterogeneous, difficult to correlate, but when you zoom right into it, it's actually not too bad, and adding the geochemistry helps quite a lot. And so this is just that top sedimentary unit. And this is that chlorite bit I mentioned that is quite clearly correlates really nicely. And especially in these two holes where you got that kind of plagioclase little bit here. But what's really interesting, I think, is that if you throw the chemistry in this bottom of the hole where it's maybe a bit more difficult to correlate, you can look at these carbonate-rich units, which are also calcium-rich, and they're stromatolitic units. So they're actually logged as stromatolite. So if you combine the geological logging, the geochemistry, and the hyperspectral mineralogy, you get a really clear correlative unit between the three holes. And this is just showing, this is that core view, the stromatolitic unit, and how if you look at on the core scale, the TSA outputs, the blue is calcite, and it clearly, or carbonate, sorry, it clearly picks it out. So if you're looking for these units, you can just go to every section that's carbonate rich and look at the core imagery, and there you have, you know, a 50 centimeter bit of stromatolite. That's 2.6 or so billion years old. It's pretty exciting stuff. And this is just for fun. This is an XRF map of that same stromatolite unit showing the really intricate kind of morphology of it. This is our Maya mapper instrument. And what's really interesting about this actually is this bit here, this kind of like little massive, well, little like really fine grained pyrite rich thing. And that you can correlate between all three holes if you find that one thick stromatolitic unit from the high logger data. And so if you want to get a little fancier and start looking at scalars, this is one of the more commonly used scalars looking at chlorite abundance in chemistry. So the 2250 nanometer feature plotted, the depth of that feature is on the Y, and then the color is the position of that feature. So it tells you about chemistry of the chlorites. And the thing that pops out to me is this unit right here, just below the chylena contact. So that's that section that I mentioned. It's difficult to view that contact just from the raw data, but if you look at this, there's clearly something going on where this chlorite is very different from that. It's a more magnesium-rich chlorite, and so that's a really clear stratigraphic marker that I think is quite interesting. And if you look at that in closer detail, in the chemistry, it's actually really nickel and chromium rich as well. And when you go a little bit further, looking at that nickel and chromium rich enrichment using the XRF mapping, we actually have magnesium chromium chlorites, which is quite interesting. And so this section is not just chromite bits, it's actually chromium in the chlorite. And so that's interesting both as a stratigraphic marker, but also in the context of provenance. That's clearly something kind of ultramafic-y coming in there. And so we're looking at chromite chemistry to investigate that further. And then if you want to look a little bit higher in the stratigraphy, it doesn't stick out quite as well as the previous unit that I showed you, but you can actually look at the chloride abundance in chemistry to start looking at volcanic units. And so the top part of the chylena formation here is quite, is characterized by iron-rich chlorite. And as you go lower in the stratigraphy, that changes. And if you look at the mineralized data, either looking at the immobile elements like zirconium, titanium, chromium, you can actually pick out three distinct kind of, or flow, or yeah, three distinct chemistries in the volcanic flows and correlate them across the holes. And they relate actually surprisingly well to these changes in chlorite chemistry. And you can see even these little changes in chloride abundance. Those are related to individual flows within a given kind of geochemical unit. And if you want to really investigate correlating those flow contacts, you could look at the carbonate content from the high logger data with respect to the chlorite abundance. And so this is the same plot where you've got chloride abundance on the y-axis, and then the color is the carbonate content. And all these low chlorite, high carbonate sections are actually altered flow tops, where you have calcite amygdalas and stuff like that. And so this is, you can look at different flow types. So whether you have an amygdalar flow or something with a really kind of brecciated flow top that's been altered by looking at these parameters together, which I think is pretty neat. And so if we move away from chlorite and look at the other most common kind of parameter that's looked at, which is white mica using the 2200 nanometer feature, looking down all three holes together. So you've got white mica abundance on the y-axis, and then the color is related to the wavelength range. So reds are more phengitic aluminum poor micas, and the bluer colors are more muscovitic. And the thing that sticks out to me in these 3 holes is this section here at the top of the Kailina Formation. So that's the top 100 meters of that volcanic unit. And it's got kind of a real phengitic alteration overprint, which is interesting, I think. And what's more interesting about it is it's really cryptic. I challenge any geologist to look at these 2 core trays and tell me this is more altered than that. It's really difficult to do just by looking at it, but it sticks out like a sore thumb from the hyperspectral data. So that's really useful in terms of correlating and also looking kind of at widespread alteration, because we're talking about a strike of about 15 kilometers between the 3 holes. And then if you combine that with geochemistry, you actually see that altered section has a high potassium. And so it's a more potassically altered section. And if you look above it, this gets into some of the mineral system stuff. There's actually a copper enrichment in the overlying sediments. The top about 50 meters or 30 meters above that is copper enriched. And if you look at the copper values kind of downhole, that kind of altered potassium section is a little bit copper depleted if you squint with respect to the underlying volcanics. And then if you look at that in the larger context, those 6 stromatolitic units I showed you actually sit right here. And so you've got this weird alteration signature with the copper enrichment. And so this is, if you can't even see, actually I have it here. Yeah. So if you look at the copper enriched section, they're tiny millimeter scale anastomosing copper sulfides. Like, good luck seeing that unless you're really flipping the core around, but it shows up in the mineralized data. And that's the stromatolite section I showed you there. And so you take that all together, it's actually quite reminiscent of like a sedimentary copper system. I mean, I'm not saying there's a deposit there, but that idea of hydrothermal fluids circulating through the underlying volcanics, mobilizing metals and depositing them in overlying sediments that are kind of reduced black shaly type things. This could be the sniffs of an archean sediment hosted copper system, which from an academic perspective is really interesting because they're not meant to exist because you need oxidized fluids. But then again, you have 6 stromatolitic sediments sitting right above that in what I could tell you is a restricted lacustrine environment because we've done a bunch of strontium chromium isotopes and things, but that's a whole other story. But it all started with seeing this weird alteration signature in the high logger data. And so this is just kind of a summary of what I'm showing you all. When you look at the high logger outputs on the drill core scale across the 3, even just using these 2 really commonly used scalars to look at white mica and chlorite, you can see some really interesting things about the stratigraphy and the alteration signatures. So seeing this alteration signature at the top of the Kailina, this stratigraphic marker, chemostratigraphic marker, that's really magnesium-rich chlorite that's come from some sort of ultramafic-y source, changes in or correlating volcanic flows in the Kailina Formation, and even in looking at changes in the composition of the underlying hardy conglomerates, where you've got you actually have a change from like more iron-rich chlorites, which looks closer to what you see in the Mount Roe basalt, to something that's more magnesium-rich above that. And you see that same change in conglomerate alteration or chemistry in the white micas. And the gold actually sits here in this section here that looks mineralogically quite different than the underlying rocks. And you can also see, for instance, in the basement here, variable alteration in the white mica, as well as some of the other hyperspectral mineralogy. That's quite a lot from 2 parameters. When you put that together on kind of a transect scale, you can start saying things about basin architecture. So that really thick section of Hardy is telling us that, you know, we're sitting closer to the basin floor, whereas the other holes are more on the margins. And we can see evidence for basin scale or sub-basin scale hydrothermal systems where we know there's some hydrothermal mobilization of gold in this hole at the base. And we see the same, well, similar alteration mineralogy and footprints in the basement here. We actually did some mine mapping and found some gold. So we know there's gold moving through the basement. and also something going on here at the Kailina-Tamiana contact where they had those base metal targets, but also where we're seeing this alteration in copper deposition. So that's that. Now just a little bit of one fun slide for the end. I think one of the cool things about having these concurrent data sets at the same scale is that you can do some fancy data things. You can call it, technically it's machine learning, I think. But I say that with a grain of salt when it's coming from me. So PLS modeling is a partially squared method. Basically allows you to predict if you have training data, develop a model and then predict another parameter from that. So just as a quick proof of concept using these drill holes, because you've got two next to each other with similar stratigraphy, both with geochemistry and mineralogy at the same scale. I used this drill hole as a training data set and developed a model to predict, well, I tried potassium, strontium, chromium first, and then used that model to predict those values for the second drill hole. It worked really well. And that's mainly because it's really easy to explain why that's happening. The potassium is related to white mica and K feldspar contact. Strontium is related to plagioclase content. Chromium is basically that chlorite-rich chromium section. It predicts that really well. And then I thought I should try something more complicated, like a geochemical index that's less easily explained by two single mineral phases or one single mineral phase. And so I tried titanium over zirconium. And even though the R-squareds aren't excellent, the modeled values, so this is based on the modeled titanium and zirconium, it's modeled from the thermal infrared spectra. It actually looks pretty good, I think. The trend is, you can see, for instance, it picks up this change in chemistry really well. You've got this section here. So this is just a quick example of what you can do. I think it's not perfect, but because I'm a geologist and I like to visualize things in their drill hole context, it's an easy way to compare the model versus the actual data, and as a bit of a proof of concept. And so in summary, with this case study, I hope I've shown you guys how you can use hyperspectral data to correlate stratigraphy, in this case, the Fortescue group, over 15-kilometer strike from just 2 drill holes, and how much value that can give you in terms of understanding alteration, stratigraphy, mineral systems, and how when you add geochemical data to that, you can add a lot of value to the hyperspectral data in terms of, again, provenance, correlation, and new base metal prospectivity in that area. And then if you have those data sets together, you can do some playing around with using advanced data analytics to, for instance, predict geochemistry from spectral data. Or like Karsten said, if you have any 2 data sets like that at the same scale, you can pretty much predict whatever parameter you feel like, if you're careful with your training data and whatnot. Anyways, that's it. I'm open to questions.
Does anyone have any questions? If not, we'll move straight over to Karsten. If not, we'll have a few minutes at the end in case you come up with anything in the meantime. Okay.
Okay, then I will share my screen again. Okay, good. Okay, so another case study. That's the last presentation for today, I guess. Just need to remove the screens around a little bit. So we're going to look at the Greenbushes lithium deposit and also how to use reflectance spectroscopy for exploration and characterization of LCT pegmatites. So in this presentation, I'll cover why lithium, and then also talk a little bit about the pegmatite at Greenbushes, how that looks like. Present some spectra, reflectance spectra of lithium-bearing minerals, and we look into another NVCL data set collected from Greenbushes deposit. And we look at some chemometrics, like similar to what Jessica just presented about with the PLS model. And then some summary. So why lithium? Well, that's quite obvious maybe, but just as a summary, so it's a core ingredient in rechargeable battery chemistries. And there are 2 main sources of lithium at the moment. From hard rocks, it's mainly spodumene. And then there are these lithium-enriched brines. There are also other sources such as lithium micas, lepidolite, and so on, but they're not really that much exploited because spodumene is just easier to process. lithium is considered a critical element, then we might wonder sometimes why not people are doing more research into it, or why not more people are exploring for it. At the moment, actually, the prices crashed for lithium because it happened so to be that Australia supplied too much lithium to the market last year, and so the prices dropped, and that means exploration is dropping. But there's a problem with that, because according to some recent summaries here by Best and Vernon from 2020, if the projected demand of lithium displayed on the right-hand side here on this diagram, if the projected demand of the electric vehicle industry would is like there displayed, then it would exhaust all of the world's known reserves by 2040, which is not that far away. So maybe there's a good reason to continue exploring for lithium deposits, and we also want to explore for the right lithium deposits. Not every lithium deposit is a good one. More about that later. The projection, many people say also that lithium, there's lots of lithium in brines in South America. That's all good, we can get it from there. But the problem is it's actually not that easy to generate that right material from the lithium bearing brines. Yeah, to process that is not that easy. So in the end, there's actually a low cost differential between the hard rock derived lithium and the brine derived lithium. Yeah, in the end, it's roughly the same costs associated with that. Greenbushes is quite phenomenal, and we're actually quite lucky that we are so close here in Perth to Greenbushes. It's just basically 3 hours down the road to the south. And I think it's the largest single hard rock lithium source, at least for spodumene concentrate. And it also has an unusual high grade of lithium. It's 2.25% up to 2.25% lithium oxide, which is not normal. Normally it's around 1 to 1.5% of lithium in these LCT pegmatites. What I also just recently found out, and is a little bit disappointing with, so the product specifications for commercial spodumene concentrates, they preclude other lithium mineral contaminants. So the clients that are after the lithium, they would just coarse grained spodumene. They don't want any lithium micas or petalite or any other funny minerals really. So what's happening is that lots of lithium actually is lost and is put on a dump. For now, on the waste dump, 30% of it, up to 40 or 50% even in some deposits. The processing of lithium also is quite energy intensive, especially if you don't have just the nice coarse-grained spodumene. And yeah, the feed rates are dependent on the particle size. So grain size is an important aspect as well. So it's not like easily said that we've got enough lithium, or like Elon Musk said, there's enough lithium in the seawater. Well, it's good, but you can't really get to it easily. Yeah. LCT pegmatites, what are those guys? So there are different kinds of pegmatites, and the vast majority of them don't contain these raw element, or the ones that we are interested in. It's only 1%, less than 1%. And these raw element, not raw earth, but raw element pegmatites can be split maybe into these lithium, cesium, and tantalum pegmatites like LCTs. And the other group is niobium, yttrium, fluorine pegmatites. And the location of those ones, a little bit biased, this map, but it's from WA, from Western Australia. And you see here the location of different operating mines, and the ones that potentially contain either lithium, cesium, tantalum, or niobium is displayed here in yellow, and then compared to all the other pegmatites. So there are heaps of pegmatites around, but not every pegmatite contains lots of spodumene and lots of lithium. The Greenbushes pegmatite is quite special, as I said before. This one intruded quite a long time ago, 2.5 billion years ago, into southwestern part of Australia, nowadays Australia, and it intruded an amphibolite mainly. That's the main contact. And the main rock-forming minerals are quartz, albite, microcline. There's lots of muscovite and schorl, which is but sometimes lithium-bearing tourmaline. There's not too much lepidolite around. There's some, but not, well, it's questionable if there's actually lepidolite, I would say. Other mafic rock alteration minerals are amphiboles. Then we've got some lithium-bearing some of them lithium bearing like holmquistite, otherwise epidote, chloride, biotite, and calcium plagioclase. And the ore zones, it's quite interesting. It can be green bushes there can be 3 ore zones can be distinguished. The lithium ore zone with up to 5% lithium oxide, which is pretty cool. That's mainly spodumene and quartz. It's associated with albite zones in the pegmatite, but then there's also a sodium zone and the potassium zone. And you see that on the sketch on the right-hand side. Find my mouse again. So it happens to be that the pegmatite intruded the amphibolite, and then it also was under some deformation, and the deformed parts of the pegmatite actually have a finer grain size and so on, and the better quality ore is the underformed part of this pegmatite. And you see the different ore zones here. The lithium zone is mainly at the rim, at the contact to the sheared amphibolite, here in this brownish tone, and then we've got this potassic zone and sodic zone here in gray. Yeah, I said the rest before, so that's all good. So what can spectral sensing do for us in LCT pegmatites? We can work on an accurate identification and quantification of lithium and its host minerals. There are also a number of geometrological applications. That's why I talked about this at the beginning of this presentation also so much about. We can distinguish spodumene from petalite, from holmquistite, from elbaite, from all the other funny minerals, and can quantify it if we calibrate data with some quantitative XRD or ChemScan, for example, some separate information. We also can quantify the minerals that we don't want or compounds that we don't want, like calcium carbonates. And we can also maybe work on grain sizes. There's a question mark there because we haven't actually done it yet. But we know from other studies on other minerals, on quartz especially, that you can estimate the grain size from especially the thermal infrared reflectance spectra quite nicely. So there are some certain bend ratios that you can apply, and it should be possible to do the same for spodumene. We just need a project sponsor to do the case study. The advantage of spectral sensing is also the data collection is quite rapid. So with the high logger drill instrument, we're collecting 1 drill core tray in 4 to 5 minutes. So you can collect lots of data quite quickly. It's non-destructive also, which is another benefit. We don't destroy the evidence here. And it can be quite reliably automated, the data processing. We have a number of mining companies. I didn't talk about this during the introduction, but there are companies that basically collect reflectance spectra day in, day out, and they just put that into their workflows, into their machine learning, and apply some standard algorithms to extract their parameter of interest, which could be the white mica composition or the chloride composition or something like this. Good. Some pictures of the people that are actually doing the work. So we've got here on the left-hand side the crew from the Geological Survey of Western Australia, led by Lena Hancock, and they are looking after the high logger. These guys are collecting data every day and processing these data and then putting up on the portal for every one of us to use for free, which is quite nice. So thanks to those ones. And this is a picture of Monica and Sophie, her student, honor student Sophie, where we went to the field around green bushes and did some sampling at the spot, basically on the regolith around green bushes. So these are the kind of technologies we are using to collect reflectance spectra in lithium deposits like at green bushes. And here are some spectra. This is more for the spectral nerds, but actually it's something new also, because there is really no summary of reflectance spectral signatures of lithium bearing minerals. So we're doing something new here. We're creating spectral libraries also that we can use then to train new collections of reflectance spectra and trying to automate the interpretation of the mineralogy. So here on the left-hand side, you've got here, on the top left, you've got here spodumene and thermal infrared reflectance spectra. So these are all thermal infrared reflectance spectra, starting from about 7,000 to 14,500 nanometers. And spodumene is a pyroxene, so it's a typical pyroxene spectrum. Then we've got petalite here. Elbaite is a tourmaline, it's a bit of a special one. I show one more slide about that soon. And then here on the right-hand side, we've got all the sheet silicates, lepidolite, for example, polylithionite, zinwaldite. And you see that the spectral signatures of all these lithium-bearing minerals look quite different. So we can quite easily distinguish them even in mineral mixtures. Works quite well. And yeah, we're working on a spectral reference library. Monica is looking after that, Monica Legrand. I might point out here this feature around 11,500 nanometer, which is not an absorption feature because we are actually in the thermal infrared. In the thermal infrared, the peaks are the absorption features, and the troughs are basically, like, let's say, are not the absorption features. They are not related to any molecules. That's basically what's left over in the spectrum. But this feature is quite useful for tracking the spodumene content, and we're going to look at that later on in a bit more detail. I highlighted here, I took this just out of the a snapshot of a screenshot of Sophie Roleta's thesis, who just submitted now recently, working on the Greenbushes tourmalines also. And we looked at the, I'm showing this because she did here a comparison of some tourmaline fragments that we found in the regolith samples compared to some standard or a reference sample of a tourmaline from Greenbushes, yeah? And just to show how similar they are, so we can actually then join the dots and understand what we find in the regolith material has something to do, again, with what's in the primary rock further down, or in the ore, basically. And yeah, we're working in the moment on these band assignments because that's not really clear from literature what's going on here, actually. But we are pretty sure that these are lithium-bearing tourmalines. Good, and some more spectra, this time from the midwave infrared. This is also a little bit of a frontier area because not many people have worked on the midwave infrared part of the spectrum. So it's all part of this setting up the reference library of lithium-bearing minerals. And I might just point out that there is, according to literature at least, a quite distinct absorption feature around 2,670 nanometers, which is assigned to lithium hydroxyl. And yeah, we see that in some of the lithium-bearing minerals, but we also see this in a normal muscovite. And we are doing research on what's going on here. Good. Maybe in relationship to the NVCL. So this is a screenshot again of the Discovery Portal, and that drill core. You can download the data from Greenbushes yourself, the high-locked drill core, and have a look at your leisure. So when you access these spectral data from the NVCL, you can open that in the free version of TSG, the spectral geologist software, and that's what you get then. You can look at the drill core imagery, and you can look at the downhole plots and some summary screens telling you something about the mineralogy, just a first estimate, basically. That's just a more focused view of that downhole plot, the summary screen. This is TSA-based, the spectral assistant-based, which is an automated unmixing. What we are doing here is we are throwing a random drill core, random spectral data at a spectral reference library and expect it to give us an answer. This is quite mad, actually, but it works in many cases pretty good. But it's just the first estimate. So when you see these kind of plots, automated unmixing algorithms, yeah, be careful, don't interpret too much into it, but it gives you a good first overview of the drill core. And in this case, if you look at the different colors here at the from the top, for example, we see here mainly different kinds of micas in yellow and smectites potentially in brown, which would be interesting. And at the bottom here, everything is purple, and that's the amphibolite that we are intruding. So we have the contact between the amphibolite and the pegmatite intersected here with this drill core, which is maybe an interesting point to look at. You can look at this also another way. These are all plots generated in the spectral geologist software. We can import geochemistry into this drill core data set. And this is the lithium content plotted downhole. We see there's lots of lithium here at the top, and it's decreasing a little bit further down. And this coincides actually with the abundance of pyroxene, with, in this case, spodumene. Yeah. So the spodumene is, we have roughly more spodumene at the top than compared at the bottom. And I showed before these spectral signatures of the thermal infrared of spodumene, for example, because we are using this feature at 11,500 nanometers, that one there. The relative intensity of this one to track the spodumene content. So there are various ways how you can identify spodumene content. You can use either the matching algorithm, like in TSA, or you can use certain scripts that get you the relative intensity of certain features and can estimate the spodumene content from that. You can also plot, you can generate different scatter plots in TSG in the spectral geologist software. You can plot the lithium content here on the y-axis versus this feature at 11,500 nanometer. That's typical for spodumene, and you can see this kind of diagram. What does it tell us? It tells us basically it's colored up by the quartz content. It tells us we would like to have a straight correlation between this feature here, 11,500 nanometers, and the lithium content. Doesn't work out like that, because if we're mixing quartz into it, that impacts on our 11,500 nanometer feature. Yeah, so we're getting this offset here. But if you look at the reflectance spectra, the mineralogy that's in your drill core, then it all makes sense actually if you put these things all together. And then you can do some chemometrics. If you have the geochemistry, we can, I showed before the downhole plot of lithium content. This is now when we train the hyperspectral data with the lithium content. And this is the predicted lithium content down the drill core. And yes, at the top, we see we have a little bit more lithium than further down. And that correlates somewhat with spodumene content. We've got maybe some petalite also, another lithium-bearing mineral. We've got that as well, maybe in the drill core further down, in the drill core, basically. I should say maybe each of these dots is basically one hyperspectral measurement. So if you see that here, the number, 36,168 measurements of spodumene down the drill core. That's a good representative sample number that we can work with. And the higher the dots, we would basically say the more spodumene we have. The lower the dot, the less spodumene, yeah? So we could zoom into that file now and look into these different changes, and you would see really very detailed changes of the spodumene content down the drill core. And so as we are talking about lithium, the other method, the other technology, let's say a reflectance spectroscopic method, technology to map lithium is this handheld spectrometer here, the handheld FTIR. And that's mainly work done by Monica Legrand and Neil Francis and Alex Otto, where they collected reflectance spectra with this little toy here from different deposits, from the number of deposits in Western Australia, but also from Gulamina in Mali. And then they calibrated reflectance spectra with the measured lithium content, and they got this line here, this correlation basically, and it's colored up by the different deposits, and we can see that's a pretty good, we can predict the lithium quite well with the handheld FTIR, which is really good because lithium is such a light element that we can't detect it with handheld XRF. That's not possible. You can use LIBS, but there might be issues then with the volume that we're measuring and so on. And well, the handheld FTIR provides just another way of measuring the lithium content if you have calibrated it before. But apart from the geochemistry, you get as a bonus also the lithium-bearing mineral. So you can quantify the spodumene, for example, or petalite or hornquistite, or whatever kind of mineral contains the lithium in that respective mineral deposit. Yeah. So we have got here in these different plots, on the x-axis, the measured or calculated content, calculated from geochemistry, content of spodumene, petalite, and hornquistite, and on the y-axis we've got the predicted one, applying chemometrics, applying the partial least square modeling. Okay, and I dropped this one just in as example of what is also is done in that area. So we're looking at the drill core from Greenbushes, we're looking at the regolith, and we're looking at actually a very large area across southwestern Western Australia to understand the regolith and the relationship of regolith with the potential underlying lithium deposits. So these are just some screenshots here. So we've Sophie and Monica and Louise, they put together these nice lithium maps of some piezolyths in the regolith, where we're trying to understand where's the lithium sitting. It's sitting in some of the tourmalines, like here, these highlighted yellow areas, but in the cortices of these ooites, piezolyths, Is it associated with iron oxides or with kaolinite or with gibbsite? So these are research questions we are currently working on. So in summary, lithium geochemistry is maybe insufficient to evaluate the economic viability of lithium deposits. We need the mineralogy. We want to know, is the lithium sitting in spodumene or in another mineral? We also would like to know the grain size of spodumene, for example. The bonus of hyperspectral reflectance spectra is that we can apply that multiple scales, and we can improve the understanding of lithium-bearing minerals as well as some key associated minerals like the tourmalines. Chemometrics is quite easily applied to quantify lithium as well as lithium host minerals. We need more research needs to be done on regolith material to speed up discovery of high quality lithium deposits undercover. And we're looking more and more into trying to see how we can use Earth observation for mapping pegmatites, and specifically those ones that contain lithium.
You spoke about comparing characteristic absorption features with the spectral library, so like USGS, and that we see compositional changes sometimes in the wavelengths shift. So in your experience, how often are you having to create your own spectral library for deposits? Is that kind of generally what's done? Or are you still referring always back to that, the USGS spectral library, for example?
Yeah, I think people are doing both. I guess the USGS spectral library and also Johns Hopkins and other spectral libraries are used by many people to do this automatic matching and identify the minerals. There's one issue with many spectral libraries, including ours, the one that's inbuilt in TSG, is the lack of validation sometimes. So these spectral libraries have been built over the past 30, 40 years maybe. And at the beginning, people tended to go to a museum, pick up a muscovite and say that's a muscovite. That's not good enough. More than often, actually, it's not a muscovite then, it's a different mineral, or it's just a fengite, let's say. So the validation is lacking there. So in the best case, you would set up your own spectral reference library for your deposit. If you're interested in a certain, like with the pegmatites now, that's a nice little package now, because pegmatites are so different to other rocks, especially those LCT pegmatites. You can set up a nice little spectral library designed for LCT pegmatites. And then you get the best results. If you are applying just a general spectral reference library, like from USGS or built within to TSG, then you get less accurate response. You get less accurate answers. So a specific spectral reference library is always better.
Right. Okay.
All right, Jess, do you want to comment on that? Because you were involved in quite a number of spectral reference libraries.
I suppose the other thing I was going to ask was about, are there any spectral libraries that actually contain mineral mixtures? Because that, from my experience, can get quite complicated.
Yes. There are some. Yeah, that's so the University of Winnipeg is a huge spectral library. It can be accessed on their website, but also through the Western Washington University Spectral Library. And they have lots of mineral mixtures, but they're not ore deposit focused anyway. They work mostly with meteorites and Martian samples. And so the common rock forming minerals kind of, yeah. And so they do have that, and there is validation data for most of those. So there'll be XRD patterns in geochemistry, but it's just not easily accessible. I can send you the links for it's basically 15 years of data collection in a 1,500 page Word document and a series of Excel files. And so they're working to make it all findable, which is what the Western Washington University group is doing. And so they've taken the USGS, Johns Hopkins, Jim Bell's library, and some started putting the CSIRO one all into one easy to use front end. It's on the web.
Great.
And so they do exist, and we're working on stuff like that, specifically ore deposit focused within CSIRO. So some of the problematic mineral mixtures, for instance, magnetite basically screws with everything, but is really important for or IOCG deposits and iron ore and things like that. And so we are continuing research and looking at how those mixtures impact spectra.
There's also only so much you can do with the spectral reference libraries. They're great to understand what's actually going on. in the reflectance spectra to learn. But like recently, we added lepidolite into the spectral reference library because we thought, okay, we want to map the lithium-bearing micas. Turns out that they look in the short infrared exactly the same, or almost the same. So they're indistinguishable by these reference libraries, by applying the automatic matching algorithm. I guess if you want to go to that level of detail, then you really, I would more recommend to use certain scripts to focus on certain absorption features or Gaussian deconvolution or something like this. Because there's too much overlap. Like if we are looking at a large wavelength range and just try to do pattern match, there's too much overlap in the end. So it's much more straightforward and also computationally less expensive if you focus on single absorption features.
Great. Yeah, makes sense. Thank you. So we've got a question. It says, how does local weather or climate affect the satellite or airborne response?
Yeah, heaps. A lot.
Is there anything that you can do, like post-processing, to mitigate that, or is it just a case of just fly on a different day or use satellite data from another day?
Actually better if you fly at the right time of the year. You want to fly at the right time of the day. So when the sun is nadir, basically orthogonal to the Earth's surface. You want to, when you organize airborne campaigns, they usually also, let's say the area requires 2 or 3 days of acquisition, then they usually book 2 or 3 days more so that they have a time window where they can operate in, which makes it more expensive, but because they are on hold, basically on a call then. But just to get around these problems with too many clouds, too much rain or wet surface simply. So in an ideal case, you want to have no clouds whatsoever and also no high clouds. So the ones that are invisible to us in the end. You don't want any humidity, anything left on the surface basically, and no vegetation, please. So Mars is good, for example. But even though even on Mars you have atmospheric features, no, there's still an atmosphere which can cause a problem. But the Earth with lots of moisture content humidity is a challenge. Yeah.
Thank you. Was there any other questions from anyone else? Those are just from the chat.
Mm-hmm. If you guys have other questions, just feel free to send us an email. Join the NVCL LinkedIn group, because there we will announce if there are more workshops, more detailed workshops, like the one we mentioned from last week that we've done together with the Geological Survey of South Australia, was focused on the chemometrics, on the PLS modeling. And yeah, I guess we're going to do another of more specialized workshops, how to write, for example, a script to extract a certain absorption feature and these kind of things. Yeah, so more specialized. And we also will try to put together more training videos that we put on YouTube then. I just see there's one more comment. Yeah, Jessica?
I think we also have some case studies coming out with documentation on how to do different things, so focused on specific geological questions. So Greenbushes is looking at some of the white mica alteration. We've got one on a skarn, drill hole through skarns in South Australia. There'll be one on Ernest Henry, so looking at alteration in IOCG systems, so keeping them quite applications focused. And those will all have high logger data sets with them that are .tdg data sets, so they can be viewed in their entirety with only the viewer GSG. So if you don't have a full license, you can work with those data sets as well.
Yeah.
And I was also going to mention one more thing on the sample mixtures and database side of things. That's also a big part of NVCL, is creating an updated sample database of validated samples. And there's a huge effort going on right now to scan our entire mineral collection at CSIRO. And so if there are specific phases that are important to you or you need to know, let us know, and we can hopefully get you a spectrum, because we've got a huge sample database.
Yeah, or if someone wants to work on mineral mixtures, that would be great. Because you can imagine how many mineral mixtures we need to create now.
Once you start putting grain size in, it starts.
Yeah. So there's one more comment in there, or question about someone has operating a TerraSpec Halo, and which mineral for lithium exploration we can detect. So the TerraSpec Halo looks like an handheld XRF, similar to it at least. And they've got a little display on top, which also gives you straight away the answer, basically. They also have a spectral library in there, and they apply some matching algorithms. And it collects visible near to short-wave infrared wavelength range. So if we are collecting visible near short-wave infrared wavelength range, that means we can map, for example, iron oxides, hydroxyl-bearing minerals like clays, or amphibole or chloride, and carbonates, some sulfates, these kind of minerals. Rare earth-bearing bearing minerals, monazite, for example, could be mapped with that because of the rare earths. Yeah, but spodumene is not possible if it's because it's a pyroxene and it's nominally anhydrous, therefore it doesn't have any absorption features in the short-wave infrared or visible near infrared. But you could detect, you can try detect lepidolite, polylithionite, these kind of lithium-bearing sheet silicates, because they all absorb in this wavelength range. But I haven't seen a good summary yet about like there's lots of theoretical work and also transmission spectroscopy work on lithium-bearing minerals and lithium-bearing smectites and these weird and wonderful minerals. But it's really difficult to distinguish them from other sheet silicates. We are trying to find a way as well. The best bet in the moment, I guess, would be at 1,370 nanometers roughly. That's where a lithium hydroxyl feature should be in theory. So look for that one, I would say. And tourmalines. I forgot to say tourmalines. Tourmalines are often associated with pegmatites, and some of them might be lithium bearing. They also have nice shortwave infrared absorption features.
Do you think we've missed kind of mineralization as such because we didn't have the techniques available?
Yeah, I think so. And you see that time after time, even without spectral sensing, now people explore the same area over and over again. We have here in the Julian Craton where they found all the nickel deposits. Then a few years later, then we do projects with companies that are interested in gold in the very same area. But because they were maybe digging up the area, had a mine, and then discovered, oh, there's actually some gold underneath the nickel deposit, and these kind of things. So we are looking again at the same area, I think. So not even only at the surface, but well, of course, further down on the y-axis, the z-axis. Yeah, there's still much more that can be found. But what I'm still missing is we are still having the sledgehammer approach. So we want to find a big deposit, and we find lots of gold, for example, or lots of lithium, and then we dig it up, and that's it. I think there's much more scope for getting a little bit more sophisticated. Thinking of, before you dig it up, first think about, do we have the right mineral assemblage? Can we actually extract the stuff from the rocks, or at which costs? And can we get more clever in processing? And can we use the data that we collect during the exploration, even regional exploration? Can we use that to predict, to model, to evaluate better? That are we ending up with a resource that we can exploit a little bit more? I don't like to use the word sustainable because it doesn't make sense with mining, because it's the opposite of sustaining something. But just more efficiently, more to with less impact on the environment and more targeted, just instead of digging a big hole and getting out everything and putting 90% of it on a dump. So yeah, I think there's lots more potential for getting more clever in the way how we explore for deposits and define good deposits.
I think on the side of hyperspectral technologies and uptake and stuff, that I don't know if you're familiar with like the HYPE cycle where hyperspectral, it came up, everyone had these inflated expectations, and now they're realizing it doesn't give you exactly quantitative mineralogy. So people aren't, they're in this trough of disillusionment where people, oh, hyperspectral is not worth it. And there's a bit of that around industry because it's not something that's taught or really well understood, but it's a really quick way to get data. And we have other data sets now that we can collect, PXRF and things like that, that are also very quick. And when you bring those two data sets together, you get something that's really valuable. And I think that we're going to start seeing that happening more. Because one or the other, I mean, PXRF isn't going to solve your problems. Neither is hyperspectral on their own. But when you start bringing those together and being able to predict other more important variables around geometallurgy and things like that, that's where some of the value is going to get pulled out of this. So I think that we're probably seeing a bit of a revival, hopefully coming up where people start trusting some of the hyperspectral outputs again. But yes, I think we're hitting that slope of enlightenment along that hype scale, hopefully. Otherwise, we're all out of a job. So.
So yeah, with that, thank you again. Thank you very much.
Yeah, thanks for having us and giving us the opportunity. Yeah, let us know if you have more
Monday.
questions. Email and
yeah, take care. Okay.
Thanks.
Bye-bye.